Hello, Brian Balke again, and I'd like to welcome you to the second lecture in our journey towards reconciliation between physics and spirituality. Events involving the smallest particles are imperceptible to our natural senses. Trichotillomania, fear of small holes, was the subject of a case study during my therapeutic training. It brought up memories of looking through a microscope at the cells inside my body and reeling, bewildered, that they appeared to be mostly empty space. Shouldn't I not just collapse into nothing? In dialogue with science enthusiasts, including the Greek physicist, I find myself confronting this same kind of cognitive dissonance. The early particle theorists, confronted with wave-particle duality, tried to create explanations to justify the mathematics behind their predictions. By mid-century, Richard Feynman, subjugator of particle field theory, concluded that there was no plausible explanation. Quantum mechanics was a set of mathematical procedures, and nothing more. Lesser minds, however, continued to babble about quantum observers, Schrödinger's cat, and entanglement. These concepts inspire parables of quantum spirituality, which is deeply disturbing to anyone who knows how to calculate quantum effects. You just can't get from quantum mechanics to telepathy and precognition. But the lack of explanation is disturbing. Without it, we lack guardrails against simply adding terms to the equations whenever observation disagrees with theory. In this lecture, then, I'm going to poke at the assumptions that constrain our explanations, with the hope of revealing opportunities to create a satisfying picture of the behavior of fundamental particles. A caution at the onset in that these constraints are not always conceptual. Politics pertains, even in the purest of our intellectual endeavors. We started our journey by exploring the evolution of the ideas that we use to understand our experience. I introduced two categories. Ideas that explain our treatment of each other are the subject of spirituality, properly understood. Physics, conversely, explains the behavior of matter, or those aspects of reality whose behavior is immutable. We concluded with the concern that both disciplines have become submerged in abstractions that decoupled them from the ancient goal of facilitating creative collaboration. In this lecture, we will analyze the reigning theory of physics, known as the Standard Model. This will not be a comprehensive survey. Rather, we will be concerned with the constraints that support the idea that space is empty and smooth, for it is this assumption that stands as a barrier to acceptance of spirituality, which demonstrates that energy and information can be organized in the absence of matter. This lecture will be somewhat technical, so those already convicted in their spiritual experience might wish to skip to the final lecture, in which I present a crude geometrical parable that not only explains spirituality, but also explains mass, an embarrassing gap in the Standard Model. Given that parable, I will draw correspondences with the teachings of our great spiritual avatars. In our first lecture, we identified symmetry as the principle that constrains the mathematical statements of modern physics. Einstein's relativity theory was offered as an intuitive example of the application of symmetry. Einstein's equations evolved from the proposition that their predictions should still be accurate even if the observer is moving with respect to the observed phenomenon. We then described how symmetry can be used to determine the quantum mechanical description of the interaction between light and charged particles. From there, I offered a rather airy continuation to the other interactions between the particles, currently considered to be fundamental. The perspectives of relativity and quantum mechanics have yet to be merged, but they are united by two axioms: that space is empty and that reality at this level is perfectly smooth. Let's turn our attention then to the experimental evidence for these axioms and see whether we can imagine a reality without them. The axiom that space is empty is essential to relativity. How was that assertion obtained? It was not there in the beginning. With the equations that bear his name, Maxwell explained light as an electromagnetic wave. In achieving this description, Maxwell drew upon the technology of differential equations, which assume smoothness. However, educated to a mechanical view of physical effects, Maxwell was not satisfied with this solution and sought for many years to design a machine that would reproduce the effects of his equations. To the naive student of physics, this seems natural. Other forms of wave move in a medium. Water or air are familiar. Is there a medium, then, that carries light waves? The compelling experiment was performed in America by Michelson and Morley, who published their results in 1887. Reasoning that the aether, in which the proposed medium in which light moves, must fill the empty spaces between atoms, they assumed that as the Earth changes direction as it orbits around the Sun, then a beam of light stationary on the Earth should change its speed over the course of the calendar year. Understanding that this effect would be small, they used mirrors to split the beam into two, which were eventually recombined to produce a pattern of light in dark rings on a screen. By monitoring the shifting of the rings over the course of the year, the apparatus could detect even small differences in the velocity of the split beams, which moved in perpendicular directions. In the event, no shifting of the rings was observed. As elaborated by the theorist, this excluded the existence of a stationary and incompressible aether. Space was therefore empty, and Einstein was justified in the 20th century with his axiom that no observer is privileged. We should pause here, however, to recognize the strangeness of stationary and incompressible. We don't expect, for example, that the speed of sound would change as the Earth traveled around the Sun, because air is carried along with the Earth. What if the same is true of the aether? In fact, these constraints were examined, and Kudra and Wien in 1900 concluded that complete consistency with experiment could be obtained if the aether was compressible and distorted by mass. However, this seemed an unnecessary complication and has disappeared from the physics canon. Or perhaps not so much forgotten as relabeled. Experts in Einstein's theory of gravity, general relativity, speak of mass as distorting the fabric of space, and the Nobel Prize for Physics of 2011 celebrated the discovery of dark energy, a form of compressed aether that forces space to expand. I have asserted and will continue to assert that these two combine to undermine Einstein's axiom that space is empty, thereby undermining relativity as a whole. In fact, this was acknowledged by Einstein in his lifetime, who called general relativity's cosmological constant his greatest blunder. The cosmological constant has, sadly, been adopted by his successors to explain the effects of dark energy. Einstein's admission was demanded by the integrity of his practice of physics. His successors might seem to be practitioners of applied mathematics. Even a naive critic can arrive by analogy at an objection to this picture. We know that a thrown ball will be slowed by the air as it passes. The ball's energy of motion is slowly lost to sound and air turbulence. So how is it that, according to Newton's law, an object moving through the aether continues to move? Or in more formal terms, the object's energy and momentum are conserved. In fact, in certain liquids, the motion of an impurity manifests conservation of momentum. This is superfluidity, which can manifest in extremely cold liquids. Held in a container, the liquid stacks with perfect order. Having no place to go, the atoms of the liquid will be displaced by a passing impurity, circulating around it, the green arrows, before returning to rest behind it. In coming to rest, they must release their energy, and the only place to transfer it is back to the impurity, which carries on its motion. For those familiar with the Feynman diagrams of quantum field theory, This seems to correspond closely with the self-interaction of charged particles, which are constantly emitting and absorbing energy. Drawing out the analogy, conservation of momentum breaks down in a superfluid when the impurity moves faster than the speed of sound. The speed of light, correspondingly, can be thought of as the speed of sound in ether. The breakdown occurs because the zone of superfluid circulation grows ever greater with the speed of the impurity. Accordingly, as we approach the speed of sound, as we add energy to the impurity's motion, we also add energy to the superfluid circulation. The picture resonates with Einstein's conclusion that the mass of a particle increases with velocity until reaching infinity at the speed of light. This is a tangent worth following. In general relativity, well before attaining infinite mass, a particle turns into a black hole. Under the symmetries of relativity, this should also happen to a particle moving close to the speed of light. Perhaps then a black hole reflects a change in the structure of the ether, caused either by compression under gravity or the shock wave generated by a particle moving at nearly the speed of light. But then, how could our picture be more consistent with the principles of relativity than the original? If the assumption that space was empty was initially driven by mathematical convenience, what about the assertion that everything is smooth? Let's dip a little deeper into the concept and see what kinds of paradoxes arise. This is not necessarily unexpected. Quantum mechanics is full of paradoxes. We should only be concerned if those paradoxes mutate into contradictions. As implied in our reference to Maxwell's equations, the assumption of smoothness allows use of powerful analytical methods. Broadly, these include all of calculus and differential equations. More specifically, in the case of quantum field theory, we have Fourier analysis, the theory of wave propagation. As illustrated on the upper right, Fourier analysis allows us to decompose complex patterns as the superposition of waves, each with constant frequency and wavelength. In the theory of quantum particles, frequency corresponds to the particle's energy, while the wavelength or bumpiness corresponds to particle velocity. While we herald the power of differential equations, the behavior of space-time in general relativity is so complex that only very simple problems have been solved. More recently, theory and experiment have focused on gravitational waves, which are susceptible to Fourier analysis. If general relativity is computationally intractable, quantum mechanics is full of paradoxes. A quantum wave corresponds to the probability that a particle will be observed in time and space with a range of energy and velocity. When observed, of course, the particle must exhibit specific properties, which means that the wave function must collapse, in a sense, into that configuration. This collapse seems to violate the speed of light and carries implications in multi-particle systems that a measurement in one place affects a second measurement potentially light years away. This is the paradox of quantum entanglement. As if this isn't confusing enough, quantum mechanical calculations often depend upon simplifications that create confusion even among academic instructors. Let's consider an example, the two-slit experiment on the right. In this experiment, an electron emerges from a cavity on the left. Think of a pebble dropped into a lake. It enters the experimental space as an expanding set of ripples. Midway through the space, the wave impinges upon a screen with two slits. From each slit, ripples radiate outward towards a detector that measures the final position of the electron. Summing up the positions of many electrons, we can make a frequency plot of the positions, observing an oscillating wave-like pattern. So far, so good. But now turn to Einstein. No observer is privileged. What if we move with the electron? Well, this changes its velocity, which changes the spacing of the ripples, which changes the distribution in the detector. Our paradox has become a contradiction. There can be only one result of the experiment. How do we resolve this problem? Well, there are electrons in the screen. When moving with the traveling electrons, those electrons will appear to be moving in opposition with the same speed and bumpiness as in the original description of the emitted electron, but in the opposite direction. Considering both the emitted and stationary electrons, then, the relative velocity is still the same. This is significant. A proper quantum mechanical wave function includes the state of all the particles in the system. In fact, for electrons, the wave function must be anti-symmetrical, or change sign, whenever two electrons are exchanged. Given the number of electrons in the system, even writing down this wave function would be impossible. And having obtained the correct answer in the simplifying case that allows us to ignore the electrons in the screen, no one even raises the issue. Such sloppiness is at the heart of many commonly touted quantum mechanical paradoxes and contradictions, including Schrödinger's cat and wave function collapse. Given this incoherence, we should be cautious in drawing parallels with spiritual experience. Still, the technologies of differential equations and oscillating waves produce accurate predictions. But does that prove anything regarding the smoothness of the underlying reality? We can follow this assumption through the history of physics, where at every stage from the four elements to atoms to electrons and nucleons and through to quarks, differential equations and oscillating waves produced accurate calculations until we created senses such as microscopes that could probe structure in greater detail. This is actually a paradox in Einstein's career. Einstein was not awarded the Nobel Prize for relativity, but for explanations of the random motion of impurities in water and the photoelectric effect. Both used the same perspective shift. To explain observations, we must assume that what appeared to be smooth to our senses must be understood to be composed of particles at a smaller scale. Then Einstein spent the rest of his life trying to build a theory that unified all physical explanations under the assumption that space-time was perfectly smooth. Should we be surprised that he failed in the attempt? In fact, Einstein's ambition is currently being elaborated with models that treat matter as oscillating loops. Smoothness is still the rule after a fashion. To unify all the forces without creating defects in the fabric of space, the theorist must posit invisible dimensions. They hypothesized that initially everything was heated to an extent that all the forces and dimensions were interchangeable. The common metaphor is Big Bang, but as a sophisticated critic, I think that an ice cube forms in boiling water is a clarifying metaphor. To get from the initial state to the modern universe involves incredible leaps of faith that, much like miracles in the Bible, require violation of conservation laws, otherwise thought to be immutable. During this progression, the extra dimensions curl up, and the geometry of the curling has dramatic effects on the physical laws in the cold final state. The theorist recognized the precarity of biological forms, which cannot form even under small variations in the strength of the fundamental forces. In the end, we seem to exist only because the Big Bang supports the existence of an infinite number of universes. Even so, the Hubble and Keck space observatories draw the progression into question. Space is assumed to be smooth in 10 directions, of which 7 collapse into inaccessible loops. In the remaining 3 dimensions, it would seem that matter should be smoothly distributed. Considering, however, the age and distribution of galaxies, the observations just don't fit the theory. The oldest galaxies, whose images we observe at greatest distance, appear too early to have formed from primordial clouds of hydrogen and helium. So the theorists introduced dark matter to drive the clumping. Even so, we would expect galaxies to be uniformly distributed, but instead they appear to cluster on the edges of large voids, as shown on the right. Again, this is unnatural in the vanilla model of the cosmology. So, well, let's introduce another form of dark matter. To be clear, the dark matter isn't in the original theory, but an ad hoc addition. We might be excused for parroting Monty Python. They're just making it up as they go along. Furthermore, recall that the dimensional complexity is necessary only to avoid defects in the fabric of space. In reality, at the heart of every galaxy is an active galactic nucleus, or AGN, a supermassive black hole which, by definition, is a defect in the fabric of space. Furthermore, recent observations from the Keck Space Telescope indicate that the black holes existed before visible stars. The only precursors appear to be quasars, enormous eruptions of matter and energy that seem suitable candidates for AGN formation. I'm not going to hold my breath, but I'd suggest that it is time for the theorists to throw away the assumption of smoothness. Why the resistance? Well, the theorists are experts in specific mathematical technologies. Throwing away smoothness means less interest in their papers, less attention at conferences, and probably no chance at a Nobel Prize. Speaking of which, I need to pause here to restate my purpose. This presentation is not going to change the course of physics. Those with the courage to raise these points in academia will be shouted down. So don't take me as the standard bearer in that struggle. I have a different goal. I want those that choose to hope in the power of love to understand that the current generation of physicists is lost to the truth. Don't reason with them, for their goal will be only to intimidate you. Just nod your head and keep your eye on the ball, which is to tend the flame in your heart and use it to bless the world. Now back to the topic. To this point, we might be inclined to believe that it has all been a misunderstanding, that people have been doing the best they can with the tools available to answer difficult questions. We need to be clear-eyed, though. In the light of their long history of failure, why do they persist? Because, simply, there is a great deal of money involved in smashing things together and peering deep into the depths of space. The technical prowess to build these devices has no other market. If the money runs out, the program dies. So, how far would people go to keep the money coming? This is the story of the Higgs boson. To appreciate the story, we need to understand fermion zoology. Given normal conditions, the behavior of matter is defined by four fermions: the electron and its neutrino, and the up and down quarks. The fermions all have the same spin, but are differentiated by their charge, is indicated, and their mass. The charge is shown as Q in this chart. The uncharged neutrino is difficult to capture and was initially inferred because the energy they carry was missing from reconstructions of the interactions with electrons. The first indication that there might be more was the discovery of muons in cosmic rays. Eventually, in smashing particles together, heavier versions of the up and down particles were also discovered. These two sets were termed the fermion generations. Accelerator physics was driven for decades by the search for even heavier fermion flavors, culminating in the 80s with reports of the tau, bottom, and top particles. What evidence validates such a discovery? Well, from Einstein's famous E is equal to mc squared, we know that when the machine smashes together particles with an energy equal to twice the mass, it will be possible to create a fermion-antifermion pair. Since the pair is at rest, it quickly annihilates, producing photons whose energy can be measured. The gross effect is that the rates of photon production kick up at the corresponding machine energy, as shown on the bottom right. This is a simple, clean signal. As indicated by the green arrows, mass tends to increase from left to right, and every generation of charged particles is heavier than the last. Of interest, of course, is whether more generations might exist. I was in graduate school in 1987, when the top particle discovery was announced by the collaboration at CERN. The data presented in seminars surprised me. There was no photon signal. This chart is about as simple a statement of contradiction as can be imagined. The top particle doesn't look like a fermion. Over the next 2 decades, the experimental program at CERN enhanced the machine power until, in these units, it would be possible to detect fermions with masses of 10 million. I followed the experimental results as the machine scanned up from 2 million to 20 million. Nothing was seen. Then a complete surprise. The experimental team backtracked to 125,000, a value less than the power available when the top was announced. The 2-photon signal was designated as the Higgs boson, named after Peter Higgs. The Higgs boson is another ad hoc addition to particle theory. It was introduced to the fermion theory to ensure that calculations were still valid when events were looked at in a mirror. If this seems arcane, the changes demanded that space be filled with Higgs energy, in violation of Einstein's axiom that space must be empty. The formulas that Peter Higgs proposed to generate the Higgs density, I should have said, meant, however, that the Higgs should be a soft signal. The people designing detectors for the Higgs in 1987, in fact, thought that it would be nearly impossible to detect at 125,000. My judgment is that the purported Higgs is actually the top particle. What was reported as the top particle looks like a combination of W and Z bosons, which were detected in 1983. Bosons can be produced in any number, and the machine energy of the top announcement is exactly what is necessary to produce 2 Ws and 2 Zs. This 4-particle combination cannot produce a 2-photon signal, which is consistent with the reports made in 1987. What astonished me in 2012 was that the rest of the scientific community was incapable of recognizing the fraud. The Higgs signal was far too sharp, and the machine energy was achievable back in 1987. How could it have been missed when every detector since the 70s had been designed to detect photon pairs? It made no sense. But people swallowed the report on face value. Well, almost. The back and forth goes like this. CERN announces the Higgs. The Nobel Committee then announced that Peter Higgs would receive the physics prize. Before the prize was awarded, however, Carlo Rubbia, the recipient of the Nobel for the top announcement, appeared before a funding committee to assert, "This isn't the Higgs that we expected. I need $10 billion to build a more powerful machine." The Nobel Committee got word and issued a challenge. "Listen, we are about to award the Nobel Prize to Peter Higgs. Is this the Higgs particle or not?" Rubbia retracted his statement, and the Nobel was awarded. CERN then waited for 6 months before repackaging Rubbia's claim. "This looks like a techni-Higgs. Can we have $10 billion to build a bigger machine?" This may seem to be fraud on an incomprehensible scale, but remember that Bernie Madoff ran a $38 billion Ponzi scheme for years before someone thought to check that the fund was making trades. In that case, all the regulators were too busy trying to get jobs in the private sector. Scientists are not immune to grandiosity. We are protected from fraud only because other scientists have always been around to check the published results. Well, no one can check the results published by CERN. In this presentation, we've batted away the objections that support Einstein's axiom that space must be empty and smooth. This opens the door to explanations that might allow energy and information to be stored without matter. In pursuit of this outcome, we have considered the intellectual and political motivations for holding on to Einstein's axiom. This is important because, in fact, the current theory is a shambles, full of paradoxes and ad hoc adjustments in response to contradicting observations. Unfortunately, the advocates of the Standard Model have strong political motivations to resist change. With our deconstructionist background, we will adopt a more hopeful tone in our final lecture. Spiritual experience may, after all, be a part of the natural order. Finally, apologies to Richard Feynman's memory. Feynman was a gentleman, committed to pursuit of the truth. The pun offered here refers rather to his ubiquitous mathematical methods, which recast Fourier analysis to simplify the calculations of quantum field theory.